Okay, so here's a nice example, I'm not sure if nice is the right word, but there you go, I've used it now, of how to use an inverse of 3 by 3 matrix to help solve the problem. So here's some simultaneous equations. Okay, my own personal preference is to do it algebraically, so just while I think about that for a moment, what I'll probably do is I would probably, let's eliminate z. I'll probably multiply the top line by 2 and do that, subtract that, and then I'll eliminate the z, you see. That's my starting point. I prefer to do it algebraically than the matrix method, just because I don't like finding the inverse of matrix. Okay, so anyway, there you go. But we're going to do it using the inverse matrices method, okay? So if you remember from the two-dimensional problem I gave you, you write the problem in matrix form like this. So it'd be -1, 6, -2, -1, 6, -2, 6, -2, -1, 6, -2, -1, -2, 3, 5, -2, 3, 5, like that. So that's your 3 by 3 matrix. And then you'd have x, y, z, because of course that gives you that as your first line. Okay, equals and 21, -16, 24. So that's how you write it out in matrix form. Okay, and if you remember the method, we're going to find the inverse of that matrix. Okay, we find the inverse of that matrix. Then what we'll do is we'll multiply both sides on the left by the inverse matrix. Remember what I mean by on the left? So I'm going to do the inverse matrix there times that, as opposed to the inverse matrix slotted in there. Okay, inverse matrix there because I want to have that together, you see. Because I multiply on the left, I need to put the inverse matrix there on the left of that times that. Okay, so we need to find the inverse of that. Okay, now there's two ways I can do this. I can either show you what the inverse is, and you're like, yay, great, or we can just actually work it out. Let's work it out. Okay. Yeah, well, I don't want to either, but you know, sometimes these things have to be done. Okay. So there we go. Let's work out the determinant first of all. I'll tell you what. Yeah, go on, let's work out the determinant because I said that's probably the best thing you should do first of all. Okay, and I'm going to write it in here. This time I'll try not to muck it up. Okay, so the term is going to be right. -10, so plus 3, so -7 times -1, so it's 7. Yeah, and then yeah, so that's going to be 30. Subtract it's 28 times by 6. 28 times 6. Crikey. 120. 48, 168. I've got to subtract that, haven't I? Subtract 168. And then -2. That's 18. Subtract 4. That's 14. Times -2. -28. So let's have a look. So that's 168, 188, 196, -189. Which is the value I'm expecting. Don't worry. Yeah, it's kind of an awkward number. Okay. Yeah, -189. There we go. So that's the determinant of A. Done. I'm going to leave that there. Matrix of minors. So you hear sounds from me. It's like, oh, you know, why do we do this? Why? It's like, you know, never mind. So, right, that one there, I'm going to place. So it's -10 plus 3, so it's -7. What's this? 30. Subtract 2. It's 28. 18, subtract 4, it's 14. Yeah, I know I've worked those out and doing that, but doing it again. Yeah. So it's going to be 30 plus 6, 36. -5, subtract 4, it's -9. -3, plus 12, 9. 2, subtract 36, negative 34. Did I do that right? No, I didn't. I did that one, didn't I? I did 2, subtract the negative 34 goes in there. I didn't do that one. So do that. So negative 6, subtract 4, negative 10. And that one, 1 plus 12 is 13. I don't have the answer to that to check. I've just got what the final inverse is, so I'm just hoping that's right. Okay. If it's wrong, sorry. Right. So what next? Matrices of cofactors. Okay. So look, what I'm going to do is I'm just going to do the multiplication here. So plus, minus, plus, minus, plus, minus, plus, minus, plus. What's that? And then divide by negative 189. So over 189, and just get rid of these negatives there. Negative, negative, negative. Okay, then do these. Negative, negative. Get rid of that. And then these, gosh, they were mostly all negatives, weren't they? Let's just check that. See if that's right. Oh. Transpose. Transpose. You could argue that, no, I'm not going to say it. You probably said, you've got to transpose it. So these stupid things. So 7, 28, negative 14, 36, 9, 9, 10, 13, 34. You know, the number of silly things I make with this is just an indication of how uncomfortable I am with doing this. Okay, it's just so tedious. Oh, now it's changed. 7, 36, 10, 28, 9, 13, negative 14, 9, 34, 1 over 189. Yeah, so that's the inverse. Okay, great. Well, not great, but there you go. Job done, shall we say? That's one of those things, isn't it? So, you know, it's like going to the car MOT place. What do you call it? Oh, God, what is it? I can't remember. What's that stupid place in Sandvila called? The control technique. That's just a big waste of time, isn't it? Okay, this is one of those things you've got to do. Okay, flipping out. Anyway, so let's just get rid of that. Right, so that's our inverse. We're going to do that times the left hand side. Obviously, then we're left with just x, y, z, and we're going to do that on that. So I'll tell you what. Do you mind if I put it in there? 21, negative 16, 24. Just to save ourselves some space. Okay, if I had my lovely interactive whiteboard, I'd just highlight that and just shift it up, wouldn't I? But as it stands, I'm just going to do that and put in the answer here. So obviously over 189, and I'm going to get a 3 by 3 matrix in here. Okay, do I want to do those in my head? No. My mind is getting frazzled now by this. It's not difficult maths, is it? I mean, you could probably teach a good Key Stage 3 student there's nothing difficult. That's part of my issue as well. It's not challenging stuff, it's just pointless stuff at times. Okay, it's not, you know, oh great, let's have a go at this because it's really challenging. Yeah, my mind just gets okay. So 7 times, by the way, I moan a lot with these as you could probably guess. Okay, it's probably a bad thing actually, because I'm kind of teaching you bad habits, but to be honest, you know. So I reckon it's negative 189 in there. I'll tell you what, if all these end up to be multiples of 189, that would be lovely, wouldn't it? Okay, I'll just rewrite that bracket because I've got a feeling that would be a bit too squashed otherwise. So that's that. Let's do, put the bracket there because it's only going to be one column in it. That times that next. 28 times 21, subtract 9 times 16, plus 13 times 24, 756. I'll tell you what, at the same time I'm going to just, so that should be negative 1, let's divide it by 189, let's hope, 4, oh, lovely. And then the last one, this times this, so negative 14 times 21, subtract 9 times 16, plus 34 times 24, 378. I don't even need to press the divide button because I know it's going to be 2. Looks fairly right, isn't it? Negative 142. Okay. Should we just check? Yeah, let's just check. Okay. So 1, 25, subtract 4, 21. A satisfaction, I think. Deserves to be ticked off. Negative 6, that's negative 14, negative 16, 3, 2, plus 14, 24. Hey, yeah, that means it's great. Okay, that kind of confirms really that the inverse matrix must be correct. Okay, yeah. Can you imagine doing this and you're making just one set? I've already shown you how simple, how ridiculously easy it is to make one really small, simple error. Okay, and then finding that error is just like you've got to do the whole thing again, basically. Okay, so it's kind of in this is there's a bit of satisfaction when you think, yay, those are the right answers. Okay, so let's just write that solution up correctly and properly and with some sense of finality. X is negative 1, y is 4, and z equals 2. And we'll just discuss that point. Did you get that pun? We'll discuss that point. That's a point, isn't it? Because it's a lot more interesting than discussing 3 by 3 matrices. Okay, so this represents a coordinate point, isn't it? Negative 1, 4, 2, and it's a coordinate point of where these 3 intersect. Now each one of these represents a plane. Okay, again, if you've done the vectors chapter, that really helps. Okay, remember in vectors, a plane in Cartesian form is looking like this: ax plus by plus cz equals d, where a, b, c are constants. But if you write them like this, a, b, c as a vector, that represents the normal to the plane. Do you remember that? That was good fun. That was great. Okay. Vectors might be harder. I think vectors is harder than matrices, but flipping X, so much more logical, I think. That represents the normal to the plane, and that's just a constant value. Okay, so each one of these represents an equation of a plane, which makes sense. You can imagine. Okay, if you've got 3 different unknowns, okay, in an equation, they show you how the x, y, z relate to each other. That's an equation of a plane. Okay, and so what we've got is we've got the intersection of 3 planes, and they're intersecting at one single point. Can you see how that might work? It's quite difficult to visualise a plane in your head. Okay, but what I always do is I think about the 3D coordinate axes. Okay, which look like this. Okay, so here we have the x-axis. Here we have the y-axis. Here we have the z-axis. Okay, that's the best I can do for you at the moment. Okay, so you've got. I must have done this with the vectors unit. Okay, so you've got your xy plane like that. See, that's the xy plane. Then you write flat. So like that's your x plane. So your x-axis, y-axis, and then that's your z-axis. You see. So you kind of got to imagine you've got three intersecting planes, okay? You've got the whole of the XY plane, which is that. Think of it as a flat horizontal piece of land. That's your whole XY plane. So that's effectively this shaded region here, okay? And if you extend it to have the negative y-axis, okay, then you've got it over here as well. You can just, yeah, it's very hard visualising. It's even harder drawing, actually. Okay, but anyway, that's your whole XY plane. It extends sort of infinitely, like negative y, negative x. And then you've got your Z plane. Okay, now your Z plane, okay, kind of like what I use this piece of paper here. Okay, it's kind of like that, isn't it? This horrible piece of paper there. Okay, so that's your vertical plane like that. Okay, so it's another plane. Notice they intersect at right angles. Okay, and then you've got another plane which is that. Okay, if I just rotate it, it's like that. Okay, so what I'm saying is you've got one plane which is between the x and the y-axis. You've got another plane which is between the y and the z-axis, and a third plane between the x and the z-axis. Three-dimensional coordinates. Okay. On here, I've got a rather nice picture. Okay, the one I'm pointing to, just right there. Can you see that right? It's kind of a nice picture, but I can't draw one of those because I've not had enough practice. Okay, but the point I'm making is all those planes, they intersect at one point, don't they? They intersect there at the origin, and that's what's going on here. All right, you've got three different planes at different angles, yes, but they're all intersecting at one single point, and that's our answer. Okay. The next question, and the question I'm going to leave you with, is what are the alternatives? What I mean is, do they have to intersect at a single point? Do you have equations where there's no answer at all? Do you have equations where there's more than one answer? Okay, it's an interesting question, might take you a while to think about. Okay, hope you enjoyed that. Okay, I enjoyed that. It's better than flipping inverse matrices. That makes sense. That makes sense. Thank you, René Descartes, for giving us stuff that makes sense. No thanks to whoever invented inverse matrices.